All right. Happy Friday or just day 36. Anyway, all right. So today we will pick up back on river profiles and talk about hydrographs and flooding. And so just some logistics for today, right? So this is the Friday lecture for this week. I front loaded this week with lectures so that you can do Lab 9 more easily. And just a reminder of what is due this Sunday at 11:59 p.m. are Monday, Wednesday, Friday lectures, so day 34, 35, and 36, and chapter 7, and then lab 9, which is this Google Earth exercise about rivers. And I'm serious that you should start this earlier in the week. Please do not wait until 6 p.m. or 10 p.m. on Friday night or Sunday night to get this started, because it will take you some time. And if you do have questions about how to do the lab, it would be much wiser to ask them during the work week when I can answer them more easily, okay? And you can email me, but some of you have been really good about just using Teams to send me quick chats, which are really helpful because I can keep track of all of my conversations with you. So Teams is always running on my computer, and so I will look at it and just answer questions whenever I can. Okay? So let's go back into rivers, all right? And so what we finished up on at the end of class on last lecture was longitudinal profiles. So the longitudinal profile is what you'll be doing in Lab 9, where you trace the elevation of the river channel from its headwaters down along through its entire course of the river to where it empties out into a lake or the ocean. And the characteristic shape of these profiles tells us about what is going on in the river in terms of stream energy, as well as erosion, deposition, and sediment transport. And the important places that we want to look at on the river are where we have inflection points. An inflection point means where you have a change in slope, right? So if the slope here is steeper and then more gentle here between A and B, this is an inflection point. Between B and C, there's an inflection point where the stream gradient becomes steeper, okay? So these changes in the slope are important because they dictate how the river is going to behave, okay? So a couple of more things today about how river channel morphology, meaning how rivers look, is really dependent on the slope of the river channel, the discharge in the river, as well as the size of the grains or the sediment that that river is carrying, okay? So in general, the steeper the slope, the straighter the course of a river, right? Because water is ultimately going to go in the lowest point possible, right? It always follows gravity. Water flows downhill. One of the key axioms of geology, water flows downhill, is that if you have steep topography, water is just going to go straight down, and it will carve out deep, narrow channels. But when you have a more gentle channel slope, you end up with rivers that are sinuous, right? That they curve. And if you have slightly more gentle channel slopes, you end up with meandering rivers, but slightly more steep rivers are braided. This distinction also depends on the bankful discharge, meaning the amount of water flowing through the entire floodplain during during a flood. Okay, so the more higher stream flow and steeper slopes, the more likely it is that you will have a braided river, right? One where you have multiple channels where the river water is carrying a bunch of sediment downhill and creating these little islands in the middle of the river, versus a meandering stream where the erosion and deposition is isolated to point bars for deposition and cut banks for erosion, right? So we can broaden our definition of this a little bit more, right? Those are the three main types, but we can also look at these different types of rivers in like more categories, right? So we can look at rivers with longitudinal profiles that are very steep, right? So starting here on the left side, right? Oops, pointer. Okay, so these steep streams, right? You see that because the river is steeper, the water is just going to travel in the fastest direction downhill. So the channel is going to be straighter. As you reduce the channel slope between less than 2 or less than 4 or even more shallow, you end up with these braided rivers, right? Braided rivers and meandering rivers. The water is not being driven by just going downhill into a narrow valley or a narrow gorge. It is able to spread out across the landscape, right? So these channels are wider and more shallow. Okay, so this is really what you want to be looking at in the lab this week is where do you have the change from straighter, narrow, deep rivers and high mountain gorges or valleys to braided rivers to meandering rivers, right? And you can see this using your elevation profile in Google Earth, okay? So that's the main control with slope and discharge that we've explained, but we also need to consider what type of sediment is in the river, okay? So the type of sediment, meaning its size, is going to help determine how that stream behaves. So in this diagram, I'm showing the different river types, straight, meandering, and braided or anastomizing, according to the different types of sediment that they're transporting. So if a river is only carrying a suspended load, the suspended load is what can float in the water, fine-grained. You'll take on a straight river channel that doesn't have any riffles or rapids or areas of deposition, and meandering streams that are very sinuous, so really like a curved snake, and then anastomizing channels where you have large islands of sediment between small channels of water. If you have a mixed load stream where you have both suspended sediment as well as sediment that's tumbling along the bottom in the bed load, you end up with straight channels that have little riffles, so little rapids along the way down, as well as point bars and cut banks and meandering streams, and relatively small islands of sediment in a braided river channel. And if you have a channel that is dominated by bedload, and bedload is the larger component of sediment deposited or transported in a stream, right? So that's boulders and cobbles that are tumbling along on the bottom of the stream. In a straight channel, you might actually have some very like distinct straight channels, but also little point bars that form inside of that channel. And then in meandering and braided streams, you end up with large point bars of cobbles and boulders, or braided islands of sediment in braided rivers. Okay, so the other component to this diagram that is important is the relative stability. That means how quickly do these types of streams change, right? So if you have just a suspended load flowing through a river, there's not going to be a lot of change, right? But if you have all bed load, so all large boulders that are tumbling down through this river that get eroded or deposited depending on storms, they're going to be a more dynamic river system. Okay, and again, the bed load to total load ratio, right? So this is kind of showing what this diagram is, the suspended versus bed load. So A low bed load to total load ratio means it's mostly suspended load versus mostly bed load. And the sediment load and size is much higher in a bed load dominated river system. Okay, so this is an important thing for you to consider during Lab 9, right? Is you are looking at braided rivers and slightly meandering rivers in New Zealand. And in New Zealand, you have really rapid tectonic uplift and a ton of rainfall. And so you have a lot of erosion going on. So this means that in Lab 9, for the New Zealand part, you are looking at rivers that are mostly bedload dominated river systems. Okay. So as we look at rivers across the surface of the Earth, we really need to remember that these are dynamic, right? I think that, like, as humans, we get very used to looking at a river and saying, like Winooski, being like, oh yeah, the river over in Winooski, right? It's not changing very much, but that's not true, right? Rivers are constantly moving, eroding, and depositing sediment, and so if you track their path through time, they can change course. So this is a time lapse of a meandering river that's evolving in the Amazon, in the Bolivian Amazon. And what you see here is you see the river that is moving downstream like this, right? And it is depositing sediment in point bars and eroding cut banks, right? And this causes a more sinuous loop in this part of the river until eventually the river cuts off that earlier meander, right? When this happens, the stream wants to take the easiest path down, right? So this part of the river is going to jump across the meander and cut off the old meander belt in the river. When this happens, you end up with a small lake occupying that former river channel, which we call an oxbow. Right? So this is diagrammatically what's going on in that time lapse, where you have deposition and erosion of the point bars and the cut banks, and through time it meanders and meanders until eventually you get such a broad loop that erosion along this cut bank breaks through to the other side of the meander, and it steals the course of the river. And so now the river course readjusts and you isolate an oxbow lake. And so you don't have to go very far to find these in Vermont, right? So if you go skiing up to Bolton, right, and you take I-89 and you're driving along on the access road, on the frontage road, you drive by a really small oxbow lake right before you turn off to go to the ski area, right? So UVM is somewhere over here, and you drive up, and right here there is a small little lake next to the access road that's right here, and as well as the freeway, and that is a small oxbow that was filled in with water, but isolated from the main course of the Winooski River, which is over here right now. Okay. And one more point about river meanders and braided streams, right, is that we have landscapes that are dominated by fluvial erosion and deposition, and that's often where humans like to live, right? You don't want to build your house or your farm or your probably a suburban development on top of a steep mountainside slope, right? That's expensive and it's difficult, but it's a lot easier to build stuff on flat land, right? So we live in a part of the country in Vermont, or you go to school in a part of the country where there's a lot of tree cover. And so the topography that rivers have formed is often concealed beneath the vegetation cover. So this is a side-by-side image of a river in Washington State, which is also really densely vegetated. Right? The Pacific Northwest is really wet, gets a lot of rain, so there's a lot of vegetation, dense vegetation. And on the right is just the satellite image of the Sauk River. But if you measure very, very precisely and accurately the elevation of the ground surface, you peel away the vegetation and you reveal many generations of this river meandering back and forth across the landscape, carving it out. And this forms where humans choose to build houses or where we build farms. And it also is an important resource for mining, right? So you read all about sand in that article from the New Yorker. It's not a coincidence that many quarries for gravel and sand, especially up here in the Northeast, are often found around where river meanders used to be. So next time that you're going somewhere like on the way up to the Green Mountains and you see a gravel pit, you should look and think about how close you are to a nearby river. You're probably mining former river gravels. Okay. So I want to come back to longitudinal profiles because these profiles themselves are also dynamic, right? So all rivers are going to drain to their lowest point, right? So they start in highlands and the slope can change along a river longitudinal profile where there are breaks in slope, right? So what we call the course of a river, what determines where a river will go is the base level, right? So the base level is the lowest point to which a river drains on a landscape. So this is because the surface elevation of a stream, right, can't go any lower than a body of water that it goes into, right? Just like when you see like a small stream flowing into a larger river or the Winooski River flowing into Lake Champlain, right? The elevation of the river water at that point is the same as the elevation of the water in the lake. We can have different base levels on the course of a river. We can have local ones where there are interruptions in the longitudinal profile along its course, and those can be changes in slope related to geology, like if it goes over a cliff. Okay, so just like when Brad Pitt and his brother go over that waterfall and a river runs through it, right? They are going through a nick point, through a local base level change, right? You could also have a change in local base level if you built a reservoir or a dam, right? Because if you build a dam, you are causing a place where water is going to flow into more calm water, and it changes where that local base level is. You could also have a landslide, right? So if you have a big landslide that flows into a river valley, right? So if we just say we have a landslide and it flows into one of these streams and blocks it, then you create a change in base level. But ultimately, all rivers end up flowing to the ocean, right? So the ultimate base level for like the Winooski River is the Atlantic Ocean, where the St. Lawrence drains into the Atlantic, right? Or into the Gulf of St. Lawrence in the Atlantic. So that is really what controls the behavior of rivers at the grandest scale, is the ocean, okay? And these changes in base level are important, all right? So this is something that fluvial geomorphologists care a lot about, right? When the base level drops. Okay, not going to embarrass myself much more than that today. All right, so changes in base level affect the entire river, right? So when the base level changes, the stream longitudinal profile is going to adapt to that change. So what could change base level, right, is ultimately if you have a sea level rise or fall, which can be related to the volume of ice sheets at the poles, or changes in tectonic uplift along a coastline. You could also have a change in lake level, right? So Lake Champlain, it's not a static water level. If you come here in, like October, beginning of October, lake level is really low. But right now, if you go down there like I did last night, the water level is really high because you have all that input of meltwater from spring storms and the snowpack. So we have little changes in lake level all the time here at Lake Champlain, but we can also have bigger ones, right? And then also addition of removal of obstacles along a stream. So if you have bedrock, right, a cliff of bedrock, like a waterfall or rapids, you have the addition or removal of a reservoir and dam or landslides. And what's critical about this is that if you drop the base level, right, so if the sea level is lower or a lake level is lower, the stream is going to do its best to make it to that new lower base level. So this results in incision and erosion along the stream channel when the base level drops, okay? That can create what are called terraces, or flat former river plains along the sides of the river, and I'll show you that in a second. If you have a rise in base level, right, so if sea level goes up or lake level goes up, the stream is going to a grade. It's going to drop off more and more sediment right where the stream enters the new base level, and it deposits sediment. So that can change the longitudinal profile. Okay. So if we just take a look here at the Winooski River Plain flowing through Williston, along Burlington, and out through Colchester into the lake, we can actually see evidence for changes in base level of Lake Champlain, right? So let's see, where's my mouse? Where's my mouse? Okay. All right, so if we come down to here, right, so this is kind of near the airport and Essex Junction, actually. So if you look here, this is a topographic shaded relief map, right? So you're just seeing changes in slope. And then if you look up at a more zoomed in level, you can see all of the different terraces, right? These former flat surfaces where the Winooski River used to flow through, right? And then they're cut through in multiple generations until you make it down to the current Winooski River, right? So schematically, it looks something like this. You have down cutting of the river and stranded terraces along the sides of it, okay? So this is an important thing to consider for where humans are going to decide to build, right? So we, right here in Burlington, live along the edge of where the Winooski River was once eroding, right? So if you go down to Riverside Drive, where just below the Trinity campus on this side of Burlington, you find that it's a flat area, and then it steps down to another flat area, and then it steps down to the river, okay? So you are seeing the evolution of the Winooski River Plain in response to a change in local base level in Lake Champlain, okay? So now we're going to transition to talking about the main hazard and threat that all rivers pose to humans, and that is flooding, okay? So different rivers behave differently in flood conditions. So now we're going to consider, what happens when you have a river plain with a certain type of river and then you get a ton of precipitation. How is that river going to respond? So some of the most extreme river flooding events are those in braided rivers in places like New Zealand or in Alaska or the Himalaya, where you have big, steep, bedload dominated rivers. So here's the Rakaia River, a large braided river in New Zealand. During kind of normal flow conditions, right? You can see all the different channels and the large grain size islands of sediment. You can also see over here the former floodplain of this river, right? This is the inactive plains that has now been grazed over and turned into agriculture. But if you get a really big rainstorm that drops off a ton of water in the mountains, now this river plain expands and fills in with water. And this is called the floodplain, right? So the floodplain is the area and surface across a landscape that fills in with water with a certain magnitude of flooding that occurs. So flooding, right, is actually our most hazardous natural disaster for humans. It's, so far in this class we've talked about like volcanic eruptions, and when that does happen and there are humans nearby, it can be totally devastating, like in Pompeii or Mount St. Helens. But the by far largest hazard for humans is related to flooding. So this graph is showing the total number of natural disasters by year, and the color categorizes it by the type of natural disaster. Okay, the dark blue at the bottom are flooding. So a majority of natural disasters, meaning natural events that impact humans, is from flooding. And then above that, which is related to flooding, is extreme weather, right? So what causes flooding is rapid, intense rainfall. So a lot in a little amount of time. And what can cause this is you can have spring snowmelt. So if you get a ton of snowfall during one winter and then it melts out over the course of the spring, it's going to cause the rivers to rise and flood. This happens every year if there's snow in the mountains here. But what else can cause this kind of natural disaster is if you have a lot of snowfall, which is like a dense storage of water, right, frozen water, and then you rapidly melt it, you can send a wave of water downstream. And then in a lot of alpine environments around the world, right, we have glaciers, and they are constantly melting and supplying water to rivers. But during the summer, when they ablate or melt more, they can increase the amount of water flowing downstream. And as we continually raise the temperature of the planet and threaten mountain glaciers, it's causing more flooding from glacier melt. And so what we are seeing in this timeline of natural disasters from 1970 to present is kind of an interesting climate change related trend. So the green and yellows right here are all kind of related to tectonic or mass movement events. Right? So like earthquakes, there's not really much that's kind of consistent through this whole thing. There might be a year in there that's more extreme than others, but it's mostly the same. Volcanic activity might vary place to place, but it's, basically the same rate through time. But what's really interesting about this is you are seeing the big growth in flooding risk as well as extreme weather through time. So this is a manifestation of climate change and its impacts on humans. So how do we think about flooding quantitatively? Okay, so this is what we call a hydrograph. A hydrograph is a measurement of stream discharge, right? The volume per unit time through time. So when you have a flood, you get a characteristic flood peak. So what I'll walk you through right now, and this is important to understand for the lab, is what each of these terms and graphics means, okay? So base flow. Base flow is what's coming into the stream normally. So that can be surface water that's draining from other rivers, as well as groundwater that's entering the stream. So that is the lower part of the curve here, okay? In this little block stair-stepped graph right here, this is our precipitation event. So you have an intense period of rainfall, and then it takes a little bit of time for all that volume of water to make it from all the hill slopes and then into the main channel. So there is a lag time between the rise from base flow up to the peak discharge in a river. Okay? This rise from base flow to peak discharge is called our rising limb. Okay? After the rain has stopped and the water, the wave of water begins to subside in the river, you have the falling limb, and that is the slow return to normal base flow conditions. So the rising limb is much steeper, right, than the falling limb. And this is because the water is rushing down through all of the tributary streams and valleys into the river that you're looking at. And then it takes a while for all of that new water to make its way out of your drainage system. Okay? So these hydrographs are important for us to study because they can tell us about the risk of flooding for an area. Specifically, we're really concerned about the lag time, right? Because if you have a big rainfall event and you live or have a house next to a river, the lag time in the flooding to peak discharge will tell you how much time you have to get away from that river, or if you need to worry about how close you are to it. Okay. So the hydrograph and its shape depends on stream to stream, and there are several main controls on this. Okay, so we have here different hydrographs for different characteristics of a stream. So we'll start with a drainage basin. So if you have a really small drainage basin, meaning that there's not a lot of area upstream of you where water is flowing into, the flooding is going to occur faster. If the basin is much larger, right, it just takes more time for all that water to come down from the upper reaches of the stream to where you are. So there's a longer lag time for a larger drainage basin. Vegetation will affect your hydrographs, right? Vegetation is a really effective way of slowing down floods because vegetation absorbs water and prevents it from rushing downhill. So if you have a barren landscape, flood hydrograph peaks are going to be much sharper and more sudden than in a forested area. If you have a mountain valley that's really steep, right, that means water is going to rush downhill very quickly. So your stream hydrograph peaks are going to be steeper and a lower amount of lag time compared to a more gently sloped landscape. And then another really important thing to consider, especially when we start thinking about how humans affect the landscape, is the amount of impermeable versus permeable soil. Permeability just means the ability of water to flow through something, right? So an impermeable surface is something like a parking lot, right? So the more parking lots that you have in an area, the more that water is just going to rush across the surface and then into a river. Versus if you have permeable soils where that water can sink down through the soil during a rainfall event, you're going to have a less extreme flooding event. And then finally, the basin drainage network density. So if you have a bunch of little streams, right, so that the main stream that you're at down here is really well connected to all of the streams up above it, all that water is going to be able to get to you much more quickly than if you had very few streams. So the density or the number of tributary streams within an area really is important for the flood hydrograph. So this lecture is fun because I get to show you just videos of floods. So this is a flash flood in the desert of southern Utah, right? So this is good because they show, all right, we had a big monsoon rain event over this part of Utah, right? Okay, all right, wow. Look, big thunderstorm, it's dropping off a bunch of rain, right, over this dry landscape. And remember, if you have dry landscapes, you're not going to have a lot of vegetation. That means that water is going to be able to rush downhill very quickly. Right, okay. Intense rainfall, it might even be aided by orographic precipitation, and then all of this water rushes down through that landscape into a dry or mostly dry stream channel and creates a flash flood. Okay. So it's important to note here, right? I mean, is this really a problem? I don't see anything that this flood is affecting. I don't see any roads. I don't see houses or buildings, any infrastructure at all that this flood affects. It's because humans, there aren't very many people who live in this part of the U.S. And once you've lived in a place like this long enough, you know that it's not a wise idea to build anything in the path of where these rivers may go. Okay. The other factor of flash flooding in desert environments that is important to consider is that when you have really intense rainfall, it can be at such a rate that it exceeds the ability of sediment and soil to absorb water. And so you end up with a large volume of water in a short amount of time, and the only place it can go is downhill into the river channels. Okay? Let's see if there's anything else in here. Some other good ones because he just shows how much debris is being picked up. Right? So when we have flash floods in certain environments, this can be an important way to shape the landscape. You can walk across these river plains and see sediment that was brought from former floods, and most of the geomorphic or geologic change in these environments is going on very short amounts of time. These floods are infrequent, but when they do happen, they are efficient. Okay. All right, so now let's look at the flip side of flooding, is when humans decide to build stuff around them. So there's a town just outside of Washington, D.C. in Baltimore called Ellicott City. And Ellicott City has suffered from some really, really bad floods in the last couple of years. So this is from like the Memorial Day flooding event in 2018, and it shows just how much water can accumulate in a drainage network in a short amount of time, and its effect on a community. Okay, so this is the beginning of the rainfall. Right now, you see the flood level going up. Oh, flood is all the way up, carrying cars. Now it is, ripping up the forest. Here's Main Street, right? So where all the commerce in the city goes on, right? It is just ripping through this city. Okay, and not just destroying property, but right, this is a hazard to human life because this happens so quickly that people are stuck in restaurants or in shops and they don't have anywhere to go. And they've built stuff around the river to try to contain it, but when you have so much water coming in at once, there's almost no way to prevent it. And then it leaves, not only erodes and leaves a path of destruction, it also leaves behind debris. Okay. So why is Ellicott City keep flooding? Okay. So this is showing the effect of geomorphology on the effect of the landscape on river dynamics. Okay, so what we have in this part of Maryland, right, is you have the Patapsco River, that's local base level, that all of these tributary streams are going to flow into. And with more and more intense rapid rainfall events related to climate change, you drop a bunch of water over this area where you have a dense network of streams that flow into Ellicott City. So Ellicott City is built at the confluence of several small streams, right? You have high rainfall, a dense drainage network, and then you also have steep little canyons along this way, all right? Okay, so there's topography and steep topography, right? And lots of impervious surfaces. So housing developments that have been built up on the highlands here, right, where water used to flow into the ground and get absorbed, can't do that anymore. So then it rushes into these streams and it causes really devastating flooding in that part of Maryland. I'll share also a really good NPR embedded podcast that is optional, but it's really interesting, and it talks about how this has really devastated this small town and called a lot of people to question whether or not they should live there anymore, which is a pretty drastic decision to make when you think about a town that's over 200 years old. So we can use hydrographs to track the magnitude and frequency of flood events. So this is one of the most important things that the USGS, our geological survey, does, is monitor streams and how much water is flowing through them. So this is a set of graphs from the Winooski River last October when we had a really big fall rainstorm. And you can see that the base level here, right, it goes up and down a little bit, maybe like a small rainstorm on the 16th, but then there was a huge amount of water that fell in a very short amount of time. So we go from base level, the rising limb, the peak discharge, the falling limb as it went back through time. So that's just looking at like a day-to-day change in flooding. But then we can also look at a broader time scale, right? And we can look at big changes in discharge across the year and use that to think about, what is causing them. So at that same measuring station on the Winooski, we can see the effect of, late fall, early winter precipitation events that causes big spikes in flooding. And then, it gets low and low and low through the winter. And then you have a broad period of high discharge because all of the snow in the Green Mountains is melting away. And that leads to just generally higher stream flow conditions. And then it eventually peters out towards the end of September. So if we had gotten to do our labs this semester outside, we would go up to a small stream in Huntington, near Huntington outside of Richmond, and you'd get to wade around in one of these high stream flow rivers because, we're in the middle of the snowmelt period. Fortunately, we won't. So now let's talk about our largest stream flow events. And this is a video of our biggest or most recent big flood in Vermont in 2011, which was the Hurricane Irene storm. And so this dropped a tremendous amount of rain in the Green Mountains and caused a lot of damage to small towns. But we saw the biggest effects of it, most visibly, by looking at the stream flow right here, where the bridge to Winooski is, right? So you've seen this part of town a million times, maybe with higher water, but I doubt that you have ever seen the banks of the river spill all the way over onto the sidewalks, right? So typically you can walk around right here, right? That's, the part of the river that you can walk down to. And so this was a big, big amount of water that fell. Let's see, there's other. So he just kind of goes through, but here, yeah, down at the spillway, right? And if you've been down to Salmon Hole, maybe if you've gone fishing or something down there, right, you can typically walk around like all over the place down here. And we actually would go over here for a field trip, but there's no way that you could do that right now. So this is an example of a large scale flood. Okay, so to finish out your lab this week, you're going to think about the flooding frequency or recurrence interval of a flood event. So this is when, you've probably heard like a 50-year flood, a 100-year flood, a 10-year flood, okay? What does that mean? So you're referring to the recurrence interval, which is the probability, the likelihood that a discharge of a certain magnitude will be achieved in any given year. The way that you calculate this, the recurrence interval, is you take the peak stream flow, the flood from every single year on a stream gauge for the entire record that you have. And then you rank each of those floods by their magnitude, okay? So to calculate the recurrence interval, which you will do at the end of Lab 9, is you take the number of years on record, right? How long you've been measuring this, and then the rank of each flood from that from those annual records, okay? What this gives you is the recurrence interval, and it tells you if you are having a 1-year flood, a 10-year flood, a 100-year flood. And so what does that mean? So a 1-year flood is a magnitude of discharge that is highly likely to occur any given year. So that means there's a 100% chance that you'll get that flow in that river every year. So on the flip side, that means that there's about a 1 in 365 chance that it could happen any given day of the year, okay? When we start talking about 10, 100, 500-year floods, now we're talking about the likelihood based on previous observations of that magnitude of flow. So a 10-year flood means that there is a 1 in 10 chance that you could have a flood of that magnitude any year. It does not mean that there will be a flood of that magnitude every 10 years. Right? This is a probability. A 100-year flood is one that there's the probability of only 1% or 0.01 that it happens any given year. Okay? So when we then apply this thinking to rivers and the floodplains, this becomes extremely important for how humans use the land. Okay? If we understand the topography of the river, right, the floodplain, where the river is going to go during a certain discharge event, it tells us about where it is safe to build. So our government, the federal government as well as state governments have designated different floodplains where it's unsafe to build, 100-year floodplains, 500-year floodplains. This tells us about where we can put housing developments, we can build towns, and really importantly, it also tells us about how to build certain types of infrastructure, right? When you build a bridge across a floodplain, do you build it a certain number of feet above the river? That is determined by the likelihood of a certain flow through that river. And then for the consumer, right, not just like any given day that you could have a flood that comes and breaks down your house, this ultimately is manifested in insurance rates. So I know this is really boring because like you guys probably don't pay anything having to do with insurance yet, but where you choose to live and build, your house someday, you will have effects of risk that are in your insurance rates that could be related to a river. The biggest problem with climate change for humans right now is that it is changing our risk assessment, okay? So if we have more intense rainfall events combined with overdevelopment of land surfaces with impervious land cover, you are going to create changing risk for building along rivers. And last spring, we saw a really catastrophic example of climate change combined with land use mismanagement in the Midwest. And you didn't hear anything about this in the news, particularly if you live in the East Coast, but this was a catastrophic flood year when a large flood happened with the combined effect of a large snowpack in the Rocky Mountains, followed by a big wet spring storm that dumped a bunch of snow on the high plains, followed by a 70-degree day right after the snowstorm, and a torrent, a deluge of water came downstream and flooded the Missouri River and Republican River and other large rivers in the upper Midwest, and it devastated a lot of communities. So this is showing the normal course of the Missouri River, right? And the floodplain that was filling all the way out to its edges during this flood. And it caused billions of dollars in damage and displaced many people in the Midwest. It was truly a disaster. So even though floods are interesting to go look at, they do have lasting effects on how humans interact and behave with each other. Sorry this lecture was a little bit longer, but hopefully it will help you get through the lab this week.